I'm going to talk about a plugin, basically an extension for Postgres that I wrote back in 2003 called PLR. So I've got kind of two versions of this presentation. One is the presentation that I give to Postgres users, and the other one is the one that I give to our users. So here I assume everyone knows what Postgres is, but how many people here, I assume since you're sitting here, you have some idea. Can you raise your hand if you use R? So this is just a few. So other people are just mainly interested in what the capability is. So let me show you real quickly. It's one of the hard things about using R is that it's hard to Google for things when you're searching for, R command for something or other. But anyway, so the R project website is r-project.org, and one of the things that makes R kind of a very interesting language is the fact that it's very widely used and it's very extensible. So there's a page on something called CRAN, so it's just similar to Perl has the CPAN, R has CRAN, and that's where all their extensions live. And if you look, I don't know if you can see the text on this page, but it says 7,176 available packages. So they've got this really extensive system. As a package author, you basically upload your source code. An automated process vets the code, makes sure that it compiles cleanly, makes sure that you've got regression tests, make sure that you've got documentation. And if your package doesn't have all of these things, it doesn't even get published on this site. Now, one of the other useful things that they've done is, you can imagine with that many packages, it could be hard to find, well, what do I want? Which package do I want to use to do some specific type of analysis? And they've got this other thing called task views, which sort of organizes this ecosystem of packages into different areas. So if you're interested, for instance, in high performance computing, there's a whole page that talks about all the packages that have to do with parallelism, and so you can actually run R code across multiple nodes in parallel. And since you can call that from PLR, you could do that from Postgres. So that's just a quick note on the R environment. So PLR is basically glue code. Pretty much everyone here is familiar with probably PL/PG/SQL, yes? So Postgres supports an extensible procedural language, notion of an extensible procedural language, and Postgres ships with, of course, PL/Perl, PL/Python. And basically, all you do is you wrap a compiler of some sort with a little bit of C code, and it plugs that right into Postgres. So PLR is that glue code between the R language compiler and Postgres, so that you can write functions, SQL functions, using the R language. So what are some of the reasons you would want to do this? Math and statistics is kind of a specialty area, and you want to be able to leverage the people that have those skills, and although most of those people, or a lot of them these days, tend to use R. So that may be one reason you want to do it. The other thing is you can make better use of your hardware. If you got a server that's got 64 cores and 256 gigs of RAM, your data is all there too, inside the Postgres process. It's advantageous to have the processing, your analytics queries, running right there inside that same process instead of shipping the data across the network to some workstation that maybe only has 4 gigs of RAM or 8 gigs of RAM. And also, just as I said, you don't want to necessarily, if you're chugging through 1 billion records, do you want to ship that across the network in the first place? Or do you want to just spit out an answer 42 and have that go to the workstation? There's also consistency of analysis. If you let people do these kinds of analytics on a workstation, then person A may do the analysis in one way and person B might do it in a slightly different way. And you may not be getting the exact same results, but maybe the analysis is so complex that you don't even realize you're not getting the same results from the two different people. Whereas once you've got a function vetted and in Postgres, you don't typically let your users change that stuff so easily, especially on a production system. So now you've got control over the code, control over the data, and you can be sure that you're going to get the result that you want correctly each time. And of course, it also abstracts complexity in that you can, and I'm going to show you examples toward the end where you can do quite a bit, quite complex types of analysis, but you're really just calling it as a simple function call in a SQL statement, fairly short SQL statement. And as I showed you, our ecosystem is huge, so this gives you the ability to make use of that. What are some of the cons? Well, if you can do something natively in Postgres, like an average or a standard deviation, it's going to run faster using the native capability than it's going to run in R. So don't do that. And R is actually not, it's very different kind of language. So if you've never used it, it can take a while to wrap your head around how it works. So from the standpoint of a SQL programmer, learning R is a bit of a challenge. I'm going to show you again in a couple of slides one way to address that, so you could use your statistics people to kind of develop the R code and then sort of cut and paste it into PLPGs or PLR functions. For an R user, if you are an R user, it's not interactive. If you're creating a function and then running the function, it's not quite as interactive as just working right inside the native R environment. So it's a little bit more challenging to debug and develop your analysis in the first place. So in that case, what you want to do is probably do the development on a workstation using the R tools and then cut and paste it into a function once you've got it up and running the way you want it. So in terms of the way that you create this is what a function looks like inside of R. You have you give it a name, use the keyword function, tell it what arguments you're going to pass, and then it's got a body. In Postgres, this is what it looks like when you create a function. You're probably all familiar with that. In this case, whatever was in the body of that R function is really what you're going to put in the body of the PLR function. And then in older versions of Postgres, there was no support for named arguments, but in pretty much all, I guess all of the released versions of Postgres now, there are. So if you name your arguments, you can refer to them in, you can refer to them in the body of the function directly. If you don't name them, they're just going to be named arg1, arg2, and so on, based on position. So here's a simple example. Again, since most people here aren't all that familiar with R code itself, I'm not going to go into a lot of detail, but basically, DataFrame is kind of the equivalent of a table inside of R. And most of the types of analysis that you do in R end up manipulating data frames. So in this case, I'm using a data frame. I'm just going to auto-generate some data, and then I'm going to select from that. This shows you that you can use PLR function in the from clause, so it can be a set returning function. There's not enough time in a 1-hour talk to go through everything that PLR can do, so I'm just going to highlight a few specific capabilities that are of interest, I think, and then go through some examples toward the end of the talk. So this first one, I was saying earlier that what you'd like to be able to do is have your statistician who works in R develop the analysis in the first place, and then just be able to cut and paste it into a function. Well, if your statistician is getting his data from a database, he's going to use an extension to R that's called R PostgreSQL. That allows you, just like you would from Perl or Python or something else, that's basically the connector so that you can query Postgres from the language. So in this case, in PLR, I've duplicated the function names that our PostgreSQL uses in order to reach into Postgres to query data out. And so what you can do is, if in this example here, this is an example R function that's solving the so-called traveling salesman problem. How many people are familiar with the traveling salesman problem? So if you know anything about that, obviously you know that you cannot get an exact answer to this. Traveling salesman problem is what's known as NP hard. So the amount of complexity involved in getting the perfect solution is enormous. But R gives you a facility for coming up with a good answer in a relatively reasonable amount of time. And this is what it would look like if you wrote that function directly in R. And you can see I'm using this R PostgreSQL. I'm saying that's the driver I'm using. This is a connection string to connect to Postgres. Here's a SQL statement. And then I'm going to run the query basically to get a bunch of data points. In this case, since it's traveling salesman problem, I'm getting lat-long points for locations I want to go visit. And the idea is to figure out what's the most efficient order to visit those locations. And this is also going to make use of PostGIS. So this is what it looks like directly in R. And you can see on this next slide, all I really did was I replaced the create function decoration part of it at the beginning and the end, and now I've got a PLR function. So because of the fact that PLR supports those same DB driver, DB connect, get query commands, I can just cut and paste from R directly in to PLR.
Is it actually establishing a connection there?
No, it's under the covers. It's using something called SPI, which is actually more efficient than establishing a new connection because this is all happening inside of the Postgres process. If you're familiar with the way Postgres works, when you connect to Postgres, Postgres spawns a process that now is what you're interacting with. And the R interpreter is getting loaded into that same process. And then the commands that have been added to the R interpreter by PLR basically give you access directly into the database without having to do another connection.
So it's utilizing the current backend.
Right, exactly.
Can it do a remote connection?
It could.
So it's smart enough, I guess, to know that that DB connect call is referencing the existing setup as opposed to a recruiter.
Yeah, it does. So when you run this from R, you'll get this answer up here. When you run it from Postgres, obviously it looks a little different, but you get the same answer. So now I'm going to go on to aggregates. Any more questions about the R PostgreSQL stuff?
You had the distance function in R. That one. Meaning Earth distance. So it's got spherical tree and stuff built into it.
It's got that. It's got packages that can do that. So in Postgres, how many people here have ever created a custom aggregate? Did you even know that you could create your own custom aggregates? So I'm going to show you how you would do that using a PLR function. The way that works is that there's something called a state function and a final function. The state function will get called for every row in the group, and basically the argument that you pass to the aggregate is going to get passed to that state function along with the result from the last call of the state function. And then your function is going to do something with that data and then output a return value. That'll continue through the group until once the group transitions to another group, optionally you can have what's called a final function. So you can take that final thing that was produced by the state function if you want and pass it to a final function which then does some final calculation. So a good example of that is average. The state function will be doing a cumulative, will accumulate the sum and it'll count, and that gets passed through the state function, and then the final function will just do the division for you and give you an average. And you can also specify an initial condition. So this example uses something called quantile, and I'm setting it up with basically four groups. So this is going to split the data into quartiles. And as you can see, it's just a one-line PLR function. This create aggregate syntax is just standard Postgres. I'm going to tell it that I'm going to take any element. I'm going to use my array append as my state function, which basically means every element that gets passed in just gets appended to an array. And at the end, I'm going to hand that off to this PLR function that's going to take that array and calculate the quartile on it. So now when I run that, this is based on some real data that I got from a company where I worked years ago when I first developed PLR. And you can see that for each workstation, these are the quartiles of this particular process result. But what's more interesting is if you look at it with something like this, which you can also do with R. This is called a Boxwhisker Plot. And when you just look at this, it becomes pretty obvious that this one workstation is not producing results that are consistent with the other ones. So that can be really useful, because now you need to go figure out why this one is different.
The y-axis Xbar.
What's that?
The numbers on the y-axis. That's like,
These?
yeah, that's the numbers Xbar.
Well, in this, I mean, it's whatever particular data I was looking at in this case. It's some data that's collected on parts that are being manufactured. And the point here is really that, you can assume it's like a diameter of something, right? If these were diameters, then this workstation is producing a diameter that's not consistent with the rest. And for quality control purposes, you don't want that.
Can it output that box plot visually somehow?
Actually, it can, and in the examples at the end, I'm going to show you how to do that. So how many people here have used window functions? A few? So PLR is one of the few languages actually that you can write a window function. And there's a bunch of window functions that are built into Postgres, and you can write window functions in C, of course. But as far as I'm aware, PLR and PLv8 are the only two procedural language handlers that support writing functions as window functions. The idea of a window function is similar to an aggregate, but it's different. So I think I've got a graphic on this, yeah. So the idea is that you're partitioning the data, which is sort of like the groups in an aggregate, and then you have this window frame that slides through the data, and then every row that you're on you've got access to all the data that's in the window frame. So this is how you can do calculations that involve other rows in your group. And you get an output for every row of the data. So unlike an aggregate where one group boils down to a single row, in this case you're going to get an output for every row in the group, but you've got access to other data from other rows. So this is a bit of a complex example. One of the things I should have noted earlier, but I try and make these slides as complete as possible so that if you download it and you're playing with it at some point later, you can literally cut and paste off the slides. But I can't possibly go through every one of these examples in detail in a 1-hour talk. So, I'm going to skip through this a little bit, but basically at the top here, I'm just generating some sample data to work with. And then this function is going to calculate a regression. It's basically looking at, can I predict earnings per share of a company this year based on their earnings per share from last year. I'm just going to try and fit a line through that data. And in this case, this is how you write the SQL statement that makes use of the window function. And because when you're fitting data like that, you have to have enough data points for it to give you a reasonable calculation. So when I wrote this function, I basically said, don't give me a calculation unless I have at least 9 rows that I'm looking at. So that's why this is empty until we get down to here. So basically what I've done here is I fit a line, and I'm using that to predict with a window function. Okay, so now back to the examples. This first example makes use of some packages that I show you the command here that you would need to install these packages in R. This is actually another pretty cool thing about R, is that it's got a built-in command that will reach out to one of the mirrors on the internet. It'll let you pick a mirror. It'll download the source code, if you're on a Linux system at least, and it will compile it and install it into your installation. If you're on Windows, I think it will get a precompiled DLL, again, off of one of the mirrors. In this example, I'm going to download high-low close data from Yahoo, and I'm going to plot the data with Bollinger Bands and some other fancy stuff that the quants use for doing stock analysis. So in this example, you can see I'm loading, this part up here is just loading the libraries that are needed. This part here is setting up an area in memory that I can capture the graphic. So this is the part where you were asking earlier about being able to return a graphic itself. So this is going to set up a device in memory to plot the graph to, basically. This one command here, get symbols, goes out to Yahoo and gets the high-low close data. And I believe it works with, I haven't actually looked at this in a couple of years, but I believe that it supports like going out to Bloomberg and probably some other services, some of which are probably paid services if you wanted to do this, but Yahoo was free. So this will go grab the data for the symbol that I pass into this function, and then this single command here is going to do the plot that you'll see in a minute. And then these commands are just capturing that plot and returning it. So there's not all that much going on in this function. The other thing that's worth noting is you notice that this thing is returning byte A. One thing that PLR does treat specially is byte A. Is people familiar with what byte A is in Postgres? It's the native binary data type. So when you've got an argument or a return value from a PLR function that's byte A, PLR is going to assume that that binary object is actually a native R object. So this can be used in a number of interesting ways. In this case, what I'm going to do is I've got an R object, which is my image, and I'm going to return it as a binary. But the other thing you can do, I talked earlier about the fact that calculations are done in R and DataFrames. DataFrame is an R object. So if you've got some kind of analysis that is multiple stages, and in particular, if it's multiple stages and maybe stage one is takes a long time to run, but you might want to fork from that point and do either this analysis or this analysis or this analysis, all from that same starting point. What you can actually do is write a PLR function that returns the data frame and stores it in a table. And then you can take that data frame and pass it back to another PLR function that does the final calculation to spit out the result. So that can be something that's useful to save you time. So that function that I wrote, just a side note here, if you're running on a production server that's headless, at least in some of the older versions of R, it required an X Windows system in order to render the graphs. So if you don't have X Windows running, that could be a problem, but you can run basically a virtual frame buffer using this method in order to be able to render the graph on a headless server. This is, again, just about a dozen lines of PHP code. I'm making a connection. I'm running a query, and in here you can see this is my stock data PLR function, but I'm also using this thing PLR get raw, which is provided by PLR. That's a function that, as I said, I was returning an R object, which is the image. So it's basically a PNG or a JPEG image, but it's still wrapped with a little bit of stuff by R. And this get raw command pulls that wrapping off and just leaves me with the image itself. So I'm just going to run this short query, grab back the data, and then output it directly to a browser. And so when I call this PHP page, this is what I get. So for about a dozen lines of PLR code and a dozen lines of PHP code, I get this graphic based on stock data that was pulled off the internet. Any questions about that?
Does the R binary object format ever you even know anything about like the actual machine
Well, it's going to be on the same machine as Postgres.
like if you ship it back, because you could ship back that byte A to your local to another server, right?
Yeah, I've never tried that. I mean, so you're saying like if you've got like a Sun OS box and a Linux box or something, and you're going to take.
64 to 32.
Yeah, I've never seen anyone try and do that. You know, normally you're creating this object in the same machine that you're storing it on. Normally, I would definitely be worried if you were trying to move it across architectures or something like that. Okay, here's another example. Anyone ever heard of Benfords Law? Benfords Law is kind of interesting. This guy figured out a number of years ago that if you take data that comes from something where it's sort of a natural exponential growth, but a lot of things fit that, right? So sales data, census data, medical claims, expense reports, all kinds of things tend to fit this natural exponential growth. Well, if your data fits that naturally, then you can actually predict the probability that the first digit of a number is a 1 or a 2 or a 3, and you can extend that. You can say you can predict the probability that the first 2 digits are a 1, 1 or 4, 2 or whatever. And so when people are faking data, they don't tend to think about this fact. And so what you can do is use Benfords Law and apply it against their data set. And it's not going to tell you like with 100% certainty that someone is committing fraud, but it can tell you that this data set is highly unlikely, and so maybe you ought to go look at it more closely. So this can be used for auditing, and is used for auditing. So I went and grabbed some open data on the internet. There's some California energy efficiency program where people were getting rebates or something for energy efficiency projects, and I thought I would just see if I could detect any fraud in the data. This shows you where you can get that data from and how to load it into a table. And then I've implemented a data type just to facilitate returning the row. And this implements the entire calculation for the Benfords Law. And so when I call that on this data, it actually, this Z value being very, very small, basically indicates that there's not a high likelihood of this data being faked. It actually fit the model really well. So in this case, I didn't find anything to worry about. So we talked about the traveling salesman problem before. I didn't really explain it all that well, but this, the gist of it is a traveling salesman needs to visit like 50 cities, and how is he going to do that in the most efficient way so he saves gas, so it doesn't take him forever to do it. So you can imagine if you've got 50 cities kind of spread out all over a map, there's an infinite number of ways you might go and hit each of the 50 cities. But you want to do it in as efficient a way as possible. This is used in a lot of different areas. Logistics, trucking companies, land management. The guy that I worked with when we first developed this example had a PhD in forest informatics. I'd never heard of it before. But he basically is a forestry guy who has to walk out amongst the trees and collect data because the companies, the paper manufacturers, care about these huge plots of land and how the trees are growing and all kinds of other things. And he's got to go to certain places on this huge parcel of land and collect the data. And he wants to get back before midnight. Another good example, semiconductors. I used to work at a company where we made lasers for doing semiconductor lithography. If you've ever seen the way chips are made, they start with I think these days it's a 300 millimeter wafer. It's basically a round platter that's about this thick made of silicon, and they literally print the circuits on the silicon, but one wafer like this might be divided into 1,000 or more individual chips. And so you can imagine if you've got 1,000 chips and each chip is worth $100, and in a semiconductor fab, one piece of equipment will pump like 100 of these wafers through an hour. So time is big money in a semiconductor fab. If you've got to inspect these things, you don't inspect all 1,000 of them. You're going to inspect some randomly determined pattern on that wafer to make sure that the processing was good. And you want to, again, you want to do that in a very efficient way because you're trying to do this at a rate of less than 1 per minute. And there's a lot of other good examples of that. So, as I said earlier, the slides are meant so that you can cut and paste from them. So I'm not going to try and go through this in every bit of gory detail. But, I create a table called stands, which is going to have my location data in it. As I said earlier, this uses PostGIS. So I'm basically adding geometry columns. I'm populating geometry columns, inserting the data. I'm going to create a table to store my output. Another feature of PLR that I didn't manage that I'm making use of here is something called PLR modules. If you've got R code that you always want available, essentially, you can put that R code in a small table called PLR modules, which just has a sequence and a source column. And this is all in the documentation. Anything that's in that table, when R first gets loaded, will get put into the compiler. It will get compiled and basically put into the R environment. So you could have, for instance, sample data. You can have common R functions that you want multiple PLR functions to be able to call. And you can put them into this. This idea was not invented by me. I stole it from PL Tickle. The Jan Vik, who wrote PL Tickle, came up with it in the first place, but it works nicely for some things. So now you can see some of the functions that this is actually what we saw on the earlier slide for doing the actual calculation. But here are the helper functions that make all that work. And again, like I said, I'm not going to try and go through this in every bit of detail, but feel free to talk to me, send me an email if you've got questions about this later on at some point. So when I run that, I'm going to find that this is the order I should go visit these locations. It's giving me an actual, the order I should visit them, the bearing I need to go, the distance I need to go from one to the next. This was actually a simulation. This is an interesting example, actually, because for keeping track of forest fires and things like that in California, they've been using drones for a number of years. And this is, again, this is actually a real use case of figuring out where the drone should go visit in order to inspect the area. This is what the data looks like, and then here it is plotted out on a map. And so you can actually look at that visually and you can say, yeah, that's probably not a bad solution to this problem. And there are plugins for R that are available that can help you with maps like this as well. So the seismic data, this example came from a guy at University of New Mexico who was analyzing seismic events. And each seismic event is basically an array of about 16,000 floating point numbers. It just represents the waveform of the seismic event. And he actually contacted me in the first place because he was having performance problems, which I ended up making some optimizations in PLR specifically for the case where you've got a single dimensional array of numbers that are passed by value, so floating points, 8-byte floating points in modern versions of Postgres on a 64-bit machine are all passed by value. And so it turns out that the R representation of that single dimensional array and the Postgres representation are, again, essentially identical. So I put in an optimization that would just do a mem copy, add whatever decoration was needed inside of R, and it made that operation very fast instead of going through one element at a time and doing a conversion, which was horribly slow. Interesting thing here is when I was playing with this, I was also trying to figure out what the best way to load this data was. So this first function is a PLPG-SQL function to load 1,000 iterations of this data so I could time it. And it took 37 seconds. And instead, I did that again, but I used one of the built-in R methods for loading data, and then stored those objects in a table, and that ran in 12 seconds. So in this particular case, it was actually more efficient to import the data through R and then store it rather than import it directly into Postgres. But now the more interesting bits, if you want to, this looks a lot like the other example we had with the graphic. So the stuff up here is just creating the graphic in memory. I literally am just using the plot function to plot this thing out. So it's a single line that really does all the work. And then I'm capturing that graphic. And so this is what this particular earthquake looked like. But more interestingly, I'd like to do some analysis on this. In particular, what I want to do is I want to find out if this earthquake hit, how many people have heard of natural frequencies of, so a natural frequency of like a building or a bridge or something is basically based on the mechanical aspects of the building. If you were to vibrate it at exactly that frequency, you tend to get an amplification effect. So what you don't, yes, exactly. Exactly. Tacoma Narrows Bridge. Tacoma Narrows Bridge was a bridge that was built in like the I guess the mid part of the like 1950 or so, maybe earlier than that. It was in the 50s, I think. It was a bridge like over a canyon that was built, and they didn't take this into account. And then a storm came along and started vibrating it at its natural frequency, and then it started doing this, and then finally it just into the river.
Unfortunately, you did it on camera for the engineer's career.
Yeah, exactly. So you can do that with R. You can use something called a fast Fourier transform and a power analysis and calculate basically where is the energy, so based on the amplitude by frequency. And that's what this function does. It basically calculates the energy by frequency, and then when you plot that, you see this graphic. And these, although I didn't try and convert these into actual frequencies, I could have done that, and then that would let me know that at X number of hertz, that's where all the energy is, and that's what I want to avoid when I build my structure if I don't want it to fall down. But, again, this is a fairly moderate amount of code in order to produce a pretty important result. So I just have one more example. How am I doing for time? Oh, okay, perfect. People familiar with control charts? Shewhart control charts? Anyone? Because I got a lot of people, not a lot of people from manufacturing backgrounds, I guess. Control charts are a method for monitoring a process, and historically they were used for manufacturing processes typically, but I've actually applied some of this to like server monitoring. The idea, and when this was developed, computers were not readily available, so it was meant to be a fairly easy way to do the statistical calculations to figure out when a process that should be producing consistent results, but is always affected by some kind of random perturbations, when has something changed and is that thing actually going out of whack and you need to go look at it and fix it before you start making a bunch of scrap? And so I've implemented the functions here. Again, there's too much to go through in detail, but I've given you a link on my own website to the SQL that is used to build all this. And basically what you get from this is what's called an Xbar chart. So in an Xbar chart you get, this is the grand average of all of this data. These data points themselves are typically groups, so you take an average of a group and a range within a group, and they're usually small groups, like 4 or 5. So once an hour, you'll go to your manufacturing line, you'll pick off 4 or 5 parts, you'll do the measurement, you'll calculate the average of that group, you'll calculate the range of that group. They didn't even do standard deviations back then because that was too much work without a computer. And then there's some charts that you could use for basically saying, based on this data, this is where all the data should fall, in between these lines that are called control limits. And so as soon as I see a point out here, I know that something non-random has happened. And in my past lives and different jobs that I've had, I've made very great use of this kind of thing where, we had an example of this, a rod that was going into a nuclear reactor that was like 14 feet long, made of steel, and we had to cut it to a very precise length, like within a couple thousandths of an inch. And all of a sudden, the thing started seeing these wild variations, and it turned out that some guy had opened a door that he wasn't supposed to open, and this manufacturing plant is in the desert in California where it was 105 degrees, and bad parts were getting made. So you do the same thing. You can spot, basically using the range of the data within the subgroups. You can also spot that your variation is going up. So even if your average is still on track, your variation may be increasing. And you can also look at something called a geometric moving average, which just more heavily weights the more recent parts. And that's all I have. Do we have any questions? There may be a package with one now. When I first wrote these slides, I don't think that package was open sourced, but I think it has since been open sourced. Yeah, R has all sorts of time series analysis available for it. It has a lot of spatial analysis available for it. I mean, just about anything you can think of in the area of math and statistics, there's someone who's written a package for it. And a lot of the kind of cutting edge research that's going on in terms of new methods to do things, in the universities, they heavily use R. So usually the most cutting edge analysis comes out as a package on R before it's available anywhere else.
I'm starting to look at it. I used to be a statistician a few years ago. Back in the dark days. And everything I learned is obsolete. We didn't do resampling because there wasn't cheap computer time. Pearson's R is gone. Big ranges. Just right down the line. He used to think, no, you're wrong, man.
Old but not obsolete.
No, I hate to say this, but
All right.
I appreciate the real life application because, I read this morning a 8.3 earthquake hit Chile, and they evacuated 1 million people, and the initial reports are showing that their loss of life is actually very minor. And you talk about this and really seeing how it can be applied, and then using it in conjunction with other data, because they also had a tsunami warning. So how do you take all this to, and combine together to save lives as well as research?
Anything else? All right,
Where can we get the presentation?
there's going to be a wiki page, on the Postgres wiki, there will be a page put up for the conference, and all of the authors will be asked to put a link to their presentation. You can get it, I mean, if you send me an email, I'll send it to you. Actually, if you go to joeconway.com, This same presentation that I've given at other conferences are already posted there, so you can get a copy of it there too, as long as you don't mind that it talks about some other conference on the first slide. All right, thank you.